I would like to welcome you, everybody. Please take a seat and grab something to drink. So the first talk, we're actually having two today. The first is from James from IEM, who's talking about quantum games. And the second one is from Tim, who's going to make an introduction of how to use quantum computing for risk analysis of financials. So first James, welcome.
Okay, so how do I change slides? Just by pressing the arrow button.
You can use this one.
Okay, so today I'm going to tell you about making games for today's quantum computers. What's been done and why you would want to. Okay, let's just go on. So I think the best way to start is to explain first why thinking about the history of computer games and why people started making games in the first place. And the early games were made in the 1950s, and they were done mostly as demonstrations of technology, or for showcasing the technology, or for educating people about the new technology, or to do research. They weren't made really for anyone to have any fun. Well, I think this picture perfectly sums that up, of someone in the 1950s looking like they're not having any fun. So the first game, arguably, was Bertie the Brain in 1950. So these are what we would call classical games, games on normal computers. And so this was an implementation of tic-tac-toe, and it was done with vacuum tubes, and it was done with light bulbs, and it was done to take to a technology trade show and show off these new vacuum tubes. So this is really the main reason why this was made. It was to showcase the technology, to make people think about it and maybe also want to buy it. And then in 1951 there was a game called Nimrod. So this was an implementation of a pre-existing game called Nim on a computer. And in this, it was again at a trade show, again trying to sell some vacuum tubes, but he was also saying that they were built to illustrate the algorithm and the programming principles involved. So this was an example where, within the 1950s, computers were a very new technology, they were strange technology. The idea of programming them was a new idea. It was something that probably people thought as an arcane art, only to be done by specialists. And so this was an example of someone showing, look, you can make a game with it. It's not all algorithms for trigonometry or whatever. This is also something that we can revisit now that we have a new and strange technology, and programming it probably seems like an arcane art to most people. We can revisit this idea. And also they said, it may appear we're trying to, making this work. What does it say? I can't even read. It may appear that in trying to make machines play games we are wasting our time. This is not true, as the theory of games is extremely complex, and a machine that can play a complex game can also be programmed to carry out very complex practical problems. And this is something that we see in the games of today. There are a lot of types of computation involved in a game. If you can show that a game can be made, it's an example of something concrete being done that people can can get their heads around. And then in 1952, again, tic-tac-toe. This time it was the first example of a graphics upgrade in the history of computer games because it was with vacuum tubes and cathode rays. They've moved beyond the light bulb era. And this was built for human computer interaction research. So again, no fun yet. And then you come back to this picture. So IBM, back in the 1950s, made an AI, as we would call it now, that played checkers. So it was built to show that computers can also play games, and it was built also to play against the human and to beat the human. I don't think the human was probably the world's greatest checkers player, but it did beat a human. It generated a few headlines and raised IBM's stock price. And this is, of course, a technique which they revisited again in the 90s when they made Deep Blue. I think I suppose it's we, even though I wasn't making Deep Blue in the 90s. And that, of course, beat Garry Kasparov, who in this case was actually the world champion at chess. And then more recently, Watson is an AI which played Jeopardy, which is a US game show, and beat the champions at Jeopardy. So something that's recurring from history is people using computers to play games to act as a showcase of technology. IBM's done it since the 1950s. Also we saw AlphaGo recently beating a human at Go, so it's something that other people do as well. Also in the 1950s, Alan Turing made an AI that played chess, but he didn't have a stock price to raise. And then in 1962, we come to the true birth of the game industry. So we have, so at MIT, they got a device called a PDP-1, which at the time was cutting-edge computational technology, and they had to work out how to use it. They had to have an example of programming it. They had to work out what it was capable of, and a group of people decided to test their programming skills, to test the device, and to make something that was fun. And they built Space War. And if you Google Space War, there are examples of it running on emulators in browsers, so you can have a go yourself without needing a PDP-1. And so this was an example again of some of these serious applications that we saw in the 50s, so for being to understand or showcase a device, to understand how it's programmed, but it was also fun. And another thing that distinguishes it from the games of the 50s were that in the 50s they were implementing things like tic-tac-toe. And it's easier to play tic-tac-toe without a computer, for example with some paper and a pen, than it is with a computer, especially when those computers are the size of a room. In this case, you're a spaceship trying to shoot down another spaceship in the gravity field of a star. It's easier to use a computer than to build a spaceship. So this was an example of actually having unique play opportunities afforded by this new technology. Okay, so no quantum so far. So in case some people here don't know quantum, a brief introduction. To explain what a quantum computer is, really one must first understand what a normal computer is. The normal computer is something which takes a binary input. So it takes an input of some information, it processes that information and gives you an output, which is also some information. Oh sorry, not speaking into the mic. And in all cases that information is encoded in binary. And that very simple normal computation is also true for quantum computers. You have an input which is encoded in binary, you have an output which is encoded in binary, and in the middle your magic thinking box processor. The difference is in what happens in the middle, how your program is implemented inside an actual physical system. And the model we can kind of use to understand how it works in normal computers is you have your bits come in and they go through these very simple 2-bit operations which basically just compare pairs of bits. So any program you run is compiled down to a level where you just compare the values of pairs of bits and you get another bit out which tells you what the output is of that comparison. and then you move on with your computation. In a quantum computer, the basic operations, well, the bits are now encoded in quantum systems, and this allows us to not just have the states 0 and 1, but also to have other states made up of those, which we call superposition states, which is described by the laws of quantum mechanics. And it means that the manipulations that we can do are not just simple comparisons of bits or flipping a bit value from 0 to 1, but it's instead, you can have more refined manipulations. So you can have the same manipulations that you use in a normal computer, but you can also have more refined ones that aren't possible when you are restricted to just the 0, 1 values and you can't access these superpositions. So we have a different set of basic operations that we can use to build up our programs, and we can find different pathways from our input to our output. And the complexity of a computation is basically the number of these basic operations you have to do in order to go from your input to your output. And there are some problems that we would like to solve where the complexity means that even if you had a planet-sized supercomputer, it would take the age of the universe to give you an answer. Whereas with quantum computers, because we can design the algorithm so radically differently, we can find ways to have so much few basic operations that we can do it within a more reasonable time scale, like before you die. So this means that, now especially for the kind of problems where we find the speed up, well, the easiest ones are ones like they're very close to the physics of the device, so things like simulating chemistry. So that would be, obviously everything's made up of molecules, so understanding molecules is helpful, and it means we can maybe find better medicines and better fuel, but also it's good for solving optimization problems, like coming up with more energy efficient logistics. So quantum computers are basically really good. And this has been something that people have been thinking about seriously since the 80s, and it's something that has mostly been in an academic environment for all of that time. So IBM has been involved since the beginning, but even so it was a more academic part of IBM research, not the part that tries to sell anyone anything. And most of the other research happened in universities. And so if you wanted access to a real quantum device, even if you were in the field, it was very hard to do. I was a theorist, I still am a theorist. Sometimes I would come up with ideas for an experiment that could be done on actual real-life hardware, but you couldn't just do it. You would have to convince someone at a university to dedicate half of one of their PhD students' projects to doing what you wanted to do. It was kind of a hard thing. But now we're in an area where they're coming out of the lab, they're on the cloud, and you can access them quite easily. So we're using the quantum experience that IBM put online in 2016. People suddenly had access to be able to play around with these things. So this is a video. Well, there's a video form of this, but it's a very simple video. I can tell you what's happening. So here we have the laptop that you have sitting at home. This is the control hardware that sits in the lab, and this is also the device where this is the fridge. Most of this is a fridge, which is cooling down the quantum device, and then sitting at the bottom here is a small chip where you actually have your qubits. And the qubits are addressed with microwave pulses. This is what drives the actual operations on the device. And so firstly you have to work out what microwave pulses to send in here, and that's done by all this control equipment. But it's the user sitting at home with their laptop that decides what quantum program is being run. So you sit there, you write your quantum program, you press run, it goes all the way to the lab where this control equipment is, turns it into a set of microwave pulses, runs on the device, that turns it into a voltage trace, which is the output. That gets processed again in here and turns it into the binary output that you get at home. So this is something very easy to do if you go to quantum-computing at IBM.com, .ibm.com, sorry. You can do this within the time scale of this talk. So finally, anyone can use quantum computers. So what can we do with this? Well, When I first started playing with it in 2016, I didn't work for IBM, I worked at the University of Basel. And the first thing that I wanted to do, without I said, I was a theorist, but I still am. I seem to be forgetting that I'm still a theorist. But at the time, I had experiments that I proposed, and I wanted to run, and I suddenly realized, well, I can run them now. So I can just, in the course of an afternoon, run this experiment, which would previously take me lots of academic diplomacy to carry out. So that's what I did. But then there was an upgrade that you could not just use the drag and drop graphical interface that initially came with the quantum experience, but you could also address it programmatically. And when you can address it programmatically, it means you can do more complicated things. You can do something where you have a bit of program that runs and it works out a quantum job that it wants to run, and then it runs that quantum job and they give you the answers, and based on the answers you do some processing and you figure out another quantum job you want to do, and you run that. So this is the basis of some of the near-term algorithms like VQE that solve interesting problems. But it's also what you would need if you wanted to implement a game with a quantum computer. So that's basically what I tried out as soon as I had the opportunity to do so. And one of the first games I made was this quantum battleships, which I see is essentially like the quantum version of Nimrod, not in what it is, but in why it exists. Because it was basically there to just show someone a quantum program and say, look, there's no magic there, there's no weird stars coming off from this to show that this is a strange arcane art. It's just a program, and it's doing something quite simple, which is implementing a game. So often all people knew of quantum computing was the complicated algorithms, the algorithms that have been dreamed up over the course of the 90s, and the ones that had for which it was possible to rigorously prove that you could do on a quantum computer faster than a normal computer. So these often come from computer science departments and mathematics departments. They're not the most tangible and easy to understand algorithms that ever existed. And so what I thought it was nice to show someone you can just do something quite simple on a quantum computer. So the main point of this game was actually to write a blog post about how it was implemented and to give people an idea of what quantum computing was and how they might want to play around with it. And then another game that I came up with was Quantum Awesomeness, I call it. And this is because if you look at the media and you read about quantum computing, often you'll see these articles that says such and such a company has now declared that they have this number of qubits. Isn't that wonderful? But if you're in the field, you know the number of qubits isn't really that important. It's not the most important thing. Because when we try to manipulate those qubits, everything is a little bit wrong. We have imperfections. And all of these imperfections we call noise. So the amount of noise is also important. And also, on a device, when you're making a quantum algorithm, sometimes you have to take 2 qubits and do an operation which involves both of those qubits. Just like the comparisons of the bit values in the classical world, you need to do things involving 2 qubits in order to actually move forward a quantum algorithm. But you can't just arbitrarily say, I want this qubit and this qubit to interact. Typically, on a device, you have what's called a coupling map, which tells you how 2 qubits. So basically, which 2 qubits can talk to which other 2 qubits. So this is a qubit on a device. It can talk to this one, which has a 55 on it. It can talk to this one. It can talk to this one. And it can't directly interact with any others. So the coupling map, the noise level, and the qubit number are all things that are important and all work together to determine how good an actual device is. And if you know only 1 or 2 of those things, you can't really determine how good a device is and how it compares to other devices. So what I wanted to make is basically a puzzle game which the way it's implemented depends on the coupling map, and it depends on the noise, and it depends on the number of qubits. So you get a sense of what a device is like by playing it. You get a sense of how devices compare by playing it. So if you play it for a device which has 1,000 qubits that are really, really noisy, you'll see that it's just nonsense. If you play it for something that has 14 qubits that aren't so noisy, you'll see that's a lot better than 1,000 qubits that are very noisy. So again, there was an idea of having a game which teaches players something about the hardware. It's not necessarily a very fun game to play, but if someone wants to know about the hardware, then they could play a game. So kind of like a benchmark, but a more informal one. And in 2019 we have a game that I didn't make, called Cue Cards, and this was made for education. You have cards, so actual physical cards, and you play a card game, actual physical cards on an actual physical table. And these cards are the basic operations of quantum computing, and by playing them you're kind of making a quantum algorithm which tries, and every player tries to optimize something different. And then at the very end you have to run this algorithm to see who wins. And you can run this on a simulator, or you can run it on a real device, and the real device adds a bit of extra educational content because you get a sense of how the real device works, what the effects of noise are, and you can even use noise as a kind of tactic in your game. If you put down, you might want to do something which in theory does nothing, but in practice you know that it adds some extra noise which might lower your opponent's chances of winning. So again, something for education. And then, something that I've been looking at more recently is procedural generation. So this is now moving towards not just trying to educate people about quantum, but find something in the space of gaming where quantum is actually going to provide something useful and interesting which commercial game makers will actually want to use. And so there are many games that use this topic of procedural generation. So what this is the algorithmic generation of content. So sometimes you might have a game which has been handmade. Someone has decided what every level looks like and what every aspect of the game looks like. We also have games where one problem with handmade games is once you've played it, you've seen everything. People often might want to revisit it, but nevertheless, you've seen everything. Now there's also this genre of games called roguelikes in which this idea of procedural generation is especially used. And it means every time you enter a level, it's different. It might have the same aesthetics, it might have the same enemies, but it's different. So it's a new play experience every time you play it. Now this is actually quite a challenging thing to do, because you can't just have a random number generator randomly placing things everywhere, because in a level you want to be able to complete it, otherwise you're going to get annoyed. And if you've got an app like a Sudoku app, maybe this is randomly generating, so procedurally generating puzzles every time you ask for a new puzzle. Again, you have to generate ones that are solvable, or people aren't going to want to use your Sudoku app. And this can be quite a hard problem because so it's a constraint satisfiability problem. You have something and you need to satisfy certain constraints. You need certain things to, like the constraint of solvability is a very abstract level constraint, but you have certain constraints that have to be solved, and you want to kind of explore the probability space of things that satisfy those constraints. And constraint satisfiability problems are things that actually are quite hard to do using computing. These are examples of these extremely hard problems that would take billions of years to solve. And so often procedural generation has to use hacks to make sure that you don't have to wait a million years for your next level. And those hacks often involve you seeing the same thing over and over again, just in slightly different configurations. So if you have the number of devices you have that can solve some of these computationally difficult problems, then the better procedural generation you can come up with. And then a simple example of procedural generation is if you play Minecraft and you start up a new world, you get a new random world to explore, and this terrain generation is done procedurally. But often this procedural generation uses something called Perlin noise, so not the bad kind of noise you have in a quantum computer. And the trouble with Perlin noise is it makes terrain that looks like it's been generated by Perlin noise. So if you've been playing these games for too long, it no longer looks nice and engaging. It just looks like, oh yeah, more of the same. So one of the challenges in terrain generation is using cloud noise but making it look like it's not cloud noise. And so one of the things is to have nicely textured terrain. And one thing that is very easy for a quantum computer to generate, even in the near term, is interference effects. Because quantum computers are basically devices to do quantum interference effects. And so if you just run one of these quantum interference effects, you can get what could be a nice texture that you could use in terrain generation. And so this is something that we did here when we came up with a terrain generator that works in this Minecraft-like game engine. It basically just uses quantum interference effects to embed a nice texture upon what was previously an overly smooth terrain, until it's something that can create something that is unique, something that if your players become bored of Perlin noise, then now they have something unique they can look at. And this has been done, so it's very easy for people to do. So if people want to start trying quantum computing, they can very easily start with terrain generation, and it's something that can run on current hardware, either real devices or on simulators. Now, I don't think I'll go through some of these details of how it works, but the basic idea behind it is it turns images, so having a way of converting an image into a quantum program and then getting the image back out of the program. So I assign to the quantum, so if I have an image like this very simple image here of just two dots on a black background, then I have devised a way of associating that with a certain quantum state, such that if I prepare that quantum state and then turn it back into an image, I'll get exactly the image that I started with. But if I start to mess around with it and reduce interference effects, then I can start seeing other things happen. So you reduce some of these effects and you see that the brightness starts to bleed out of these 2 points. And if you do it even more, it bleeds out even more, but then you start getting interference patterns, and then at the end you have this, it's a checkerboard. So how did that turn into that because of these interference patterns? Well, because of quantum, basically. But yeah, if you stop it halfway, then you get these nice textures that you can then use in procedure generation. So this is something that you can do classically, but this is our first steps into trying to use quantum computers for procedure generation. So it's not going to be the kind of results that are going to convince game designers to pay you a lot of money to get it in their game quite yet, but these are the first steps, and they're also things that if people want to start trying out quantum computing themselves, then generating procedurally generated terrain like this is a very simple starting point before going on to more complicated things. So what I've just explained are basically all the games so far that have used actual quantum computers. There are many other games that have used simulations of quantum computers. So the reason for this mainly is that when you talk to a quantum computer, it takes a bit of time. So you send the job to a quantum computer, and you have to wait a few minutes, and then you get the result back. So if you're doing something every frame of your game, then it's going to be a very slow game. So for some people, they want to be free from this restriction of trying to deal with that lag and have something more responsive. And for that, if you're using small numbers of qubits, you can very easily do it in a simulator. So if you're wanting to teach someone about quantum, then you can implement some of the very fundamental parts of quantum mechanics on just 1 or 2 or 3 qubits, and you can simulate that very easily and incorporate that into a game. So there are many examples of this. This one is QPong, which is a quantum version of Pong. And at the bottom there you are creating a quantum program, and the quantum program that you create controls your paddle. Well, maybe this is your... so it controls your paddle. So you're controlling the paddle by adding things to your quantum program. So you don't have to wait a few minutes every time you make a move to see where the paddock is. So this is the kind of thing that would be perfect for a simulator. Okay. Another example of a game of a simulator is Qiskit blocks, which is again we're using Minetest, this Minecraft-like game engine. So it gives someone the ability to go into a familiar situation, which is like this Minecraft world, and they can build quantum circuits there using blocks as you might do in Minecraft, but in this you're building quantum programs and you're using them to solve puzzles. So it's another use of simulators to do something educational. And this of course is not something that has a parallel in the history of normal computers, because we didn't have a simulator for normal computer. A simulator for a normal computer is a person with a paper and a pen. And there are other ways to make games for that. And we also, so I should mention that software for programmatically dealing with quantum computers is called Qiskit, and we also have simple ports of Qiskit that can go these microcontroller devices. There are people who are trying to teach people programming, and often they do it by taking one of these very small computational devices, so that the barrier between learning programming and creating something nice is very small. So also you want to leverage that sort of tactic to get people to learn quantum computing. And we've got, we can make games for these very simple devices using a very simple simulator. So that's basically what I had to tell you. In the end, where did we make games for quantum computers? Well, at the moment we are recreating the 1950s, where we are making games as a way of showcasing technology or educating people about new technology and helping people understand, helping people have their first steps into using this new technology, either by learning about it or with the continuing generation. The today's generation, something very simple where people could start playing with their own versions of. What we haven't quite reached yet is 1962. So the invention of Space War. The first time that we have a unique play experience that can only be delivered by the new technology. So that is something that I'll be trying to work towards over the next few years, and hopefully I will achieve it, and we'll see what it looks like when we get it. Maybe we will follow this pathway that IBM has laid down for many decades of being somehow based on AI, with some sort of game AI. Maybe not. Maybe it won't be me that makes it. Maybe it will be you. But if you want to have a go, here are some links that might help you on your way. Okay, so that's all I have to say. Thank you.
Thank you very much, James. That was a very illustrative talk. So if you want to get into quantum, it's not easy to understand. I hope you catch a little bit of the talk. Do you have any questions? One second. I have a very fancy way of addressing questions. So, any questions?
Thank you for the talk. And maybe one question: have you ever been approached by a John comic or any other people who develop games? I mean, are there any game developers who really love this stuff because it's something so different?
Is this the one?
Use the other one. Yes.
It's a bit echoey. Is this the one I was using? Anyway, maybe I use that one.
That's even worse. So, the things is the answer. The things are quite big on game development, and the thing we're quite excited about experimenting with this new technology. So we have a game jam that we organised alongside the Finnish game jam. We have the creative Angry Birds there making an awesome game. We have a university
that has a custom game design, which is going to start incorporating custom into their course. So the Finns are definitely our biggest fans. Unfortunately, Nintendo has not yet done so. But one day, that's the aim. Okay. So, any more questions?
Any more questions?
Anyone wants me to say this in?
So, alright, then thanks again, James. I think we're going to make like a 2 to 3 minute break. Everybody can go to the restroom or take some new beers. So feel free, feel home, and then we'll start the next talk in a few minutes. So let's resume the session. Next is Tim and Felix from Accenture, making an introduction about like what else practical use quantum computing can have in not in the game industry but in the financial industry. So nope. Oh. Let's reconnect in the back. So actually, I forgot in the beginning how many people in the room are here for the first time. Okay. Interesting. Who of you heard about quantum computing before? Like, and do we have some physicists here? Okay. Mathematicians? Okay, cool. So, the idea of this meetup is to address this topic to like all of you. I know that within the time frame and on a Friday evening, it's pretty hard to understand everything here, but this series of meetups we are doing every quarter, and you are happily invited, so we are trying to like give you topics in all kind of areas to understand this technology a little bit better. So the stage is yours. Just versuch so nah wie möglich.
So, yeah, thank you very much for the invitation. Very happy to be here. And hopefully, after we get a very nice introduction of how to have fun with quantum computers, we can introduce you to another topic that gets people excited for other reasons, but maybe can also be applied besides risk analysis or simulations for finance. Actually, there are a lot of simulations that are very similar to the topics that I'll show you. Maybe a short background to me. So I'm also a physicist. I did quantum computing. I actually built one of those qubits in the lab as a PhD, and then switched to consulting and software development. We are part of a group in Accenture that does emerging technologies. So we actually look at these kind of technologies that are kind of almost ready, or will at some year be ready for the market, and then see what you can do with that stuff. That's somehow also commercially maybe interesting. And with me I have Felix. Quickly introduce me.
Yeah, thank you. So Tim and I started building up the quantum computing community in Accenture ASGR. To explain ASGR, it's how we're organized, so Austria, Switzerland, Germany and Russia. And I'm happy that from the small cell we started, as the two of us are now over 200 people in ASGR following the quantum journey at Accenture.
So a couple of other excited people. And Matthias Siegler is the guy who actually pays us for having this fun. Okay, so why are people getting more and more excited about quantum computing? Probably a lot of you, if you have had contact with quantum or heard of quantum, you also heard of quantum supremacy. So there's like a first proof that a quantum computer can do something that is impossible for classical machines. And I know that the people from IBM are discussing this. And actually I think this is also what makes it very exciting, because it's a race. You have two different kind of machines that are pushing each other, so it's like another moon race in my view. So this is really exciting. We will start a little bit with sharing a couple of short updates on what happened with quantum computers in the last year, and then we'll get into getting started with quantum software development kits. Actually, we'll play around with the IBM tools as well, and try to get a little bit into the nitty-gritty of building these registers and trying to get to a more abstract view. So today, if you use computers, normally you have like a very nice user interface, and between that there are a lot of abstraction layers. You probably know if you're a mathematician or a computer scientist or a physicist, and I try to give some intuition to parts of the stack that is already a system. But first, to you, Felix.
Yes, so probably at the beginning of this year you already heard some golden 20 jokes, and why it might be also like the golden 20s for quantum lays mostly in what happened in 2019. So I think 2019 was quite an interesting year about quantum, and there was even more buzz than probably expected. So IBM, for example, announced their 53 qubit system, and a little bit later there was some buzz also on Twitter, because a publication was leaked, I would say, and somehow it disappeared again from the internet. And the slide Tim just showed on quantum supremacy is actually quite interesting because Google claimed that they have done a very difficult calculation with some speed up. Then we had a discussion between IBM and Google again, and we see that there's also a lot of opinions around this topic, which is actually, in my opinion, good because more people start looking into the topic, and maybe this will lead to actually also more companies investing into the field. And we can see that, for example, Microsoft and Amazon also announced their cloud platforms, which might bring this more to the public. So I don't know how many people are here because they're interested in doing something at work with quantum computing. Okay, so some people, and actually quantum computing is interested for companies because of several reasons. So here are 3 reasons where companies are looking into quantum computing in order to at the end earn more money. So either by increasing revenue or by bringing down some costs, which are machine learning, optimization, sampling, and simulations, which come also with some hurdles to overcome. Another big thing is the cryptography. I think there's also a lot of buzz in this field, but nevertheless it is very interesting for companies to start looking into it and what it means for their business.
Now comes the slide that Felix always says is my most beloved one because I always show it. And the question is a little bit so how actually can we use quantum physics to make something sensible? And probably a couple of people already know this. But the big challenge with quantum computers is actually that you try to access something that has a very short lifetime. So it essentially doesn't exist. And that's also the reason why we typically have a very bad intuition for it. So our brains grow and evolved over the last 100,000 of years. Without ever really checking, seeing like quantum effects and getting used to it. And the reason for this is that actually these quantum effects live at the microscopic scale. And actually what you have to do to build a sensible quantum algorithm, you have the big challenge that, of course, you typically start with a classical implementation like a digital circuit. You encode your problem somehow. And then you have to do like a translation into the quantum world. And in quantum, it's very different. It's actually that particles behave like waves. Probably some of you have heard of the double slit experiment or so. Is that it makes a big difference if you have kind of 2 holes in the wall and you shoot a shotgun. Then behind that you have 2 lines of holes. But if you take actually something that is quantum and behaves like a wave, like a laser or something, you have behind that a very strange interference pattern where in between the two streaks of holes you have actually something. This is yet not really quantum because you can do this with waves, but it's kind of a feature of these particles. So what you actually have to do is first find some sensible quantum translation, represented in your quantum registers. And then kind of, I always say it's like throwing stones at the right place. So, because in the end, what you want to have is, again, kind of a classical result. Because if you're completely random, like the pictures that James showed, that it's kind of spreading out everywhere and it's kind of uncontrolled, then also your result is arbitrary and doesn't tell you something. So you have to design these quantum algorithms in such a way that throwing stones at the right position, these waves add up and interfere, that in the end, you only end up kind of with one spot that tells you, within the whole region of possible solutions that this water represents, you have this one that's the right one. And hopefully after 20 minutes or so, we will get a little bit into the direction to give you an idea how people designed those algorithms to help with practical problems in the future. To give a very quick repetition, bits and qubits. So typically you have a bit that has 0 or 1, so you have an error that doesn't exist or that shows to the 1, to be very simple. And if you look at quantum mechanics, you actually recognize, you also start to make it simple with a 0 and a 1. But what you can actually do is that you don't have this discreteness, but actually you can, the whole bit is characterized by a number that has a continuous value, and actually it's even true of those. So what in the end, if you control a qubit, you can kind of change these angles, and in every direction it shows it has kind of an own state. So it's a little bit like an analogous computer that can take every state between 0 and 1. The problem with analog computing is actually that you don't have any means to correct for small errors that occur. And every time you build something, there's some noise or something that disturbs your computation. And if you can't correct for these errors, it's just hopeless. And actually in quantum computers, there are some indications, and I know that James worked on this a lot, that you can actually correct for errors that happen in this quantum world. So that gives us hope that we can use those computers for something that hasn't been done before. And now we have to switch to the browser. So
Here?
very good. Thank you.
Very good. Bigger?
Can everybody can you read the numbers and text? What you also from behind there? Okay. So what I want to introduce to you now is one kind of like a few basic algorithms that theoreticians have proved if you can implement them on a quantum computer, they're much faster than the classical algorithms. And this is kind of the very theoretical approach that gives you a proven speed up. Disclaimer, there are also algorithms that are kind of heuristic. So it's a little bit like if you want to go from A to B, you can do two things. Either you sit down, you think a lot, and you find the perfect solution, which takes quite a while, but you can prove that it's the perfect solution, or you just go into the direction that is kind of somewhat right, which is a heuristic that helps you get somewhere quicker, but you're not sure if you really reach there. So if you really go to the top, actually that's already the result almost. So what I've prepared is a couple of code that you can find is actually the guys from IBM did a great job already to build a couple of notebooks that help you understand how those algorithms work. And what we'll start with, and on the very top, we start at the beginning. Thank you. Is actually using these quantum registers that James already showed you for so-called something that's called risk analysis. And what you have to do to start the full thing is first you could use something like Collaboratory, and the IPython notebook, which is some kind of interactive notebook that lets you write some markup, so explain what you're doing, and then put some code in between. And first we install Qiskit, and then I think we don't have to let it run. We scroll a little bit down, it tells you that it's a lot of packages that it installs. And you continue to import, and this is something you already also saw. You start to import the quantum circuit, and you need also a classical register in order to read out what you're doing. So typically the measurement results from your quantum computer land in some classical register. And there are a lot of visualization tools that we don't really need to know of. And what now is really interesting for us, so what is actually risk analysis in maybe 2 or 3 sentences, and I hope there's probably a couple of people from quantitative finance, so please don't beat me up. But what you want to do in risk analysis is actually that you have if you think you invested in a portfolio in a couple of assets, and the problem is you actually don't know, you have some uncertainty about the future. So you don't know if some interest rate is going up or down. There's some uncertainty. So what's a way to predict what will happen in the future? It's to just calculate it for a couple of different values of the of your interest rate and see what comes out. Yeah? And then you can take kind of an average about over all the outcomes that happen to get an idea of what is kind of the average direction what your portfolio will go into. Yeah? And what do you have to do to get to really kind of do this averaging? It's in the end it's kind of a sum or an integral. And it's very easy if you do this for one asset, but if you have a lot of assets and a lot of different variables that influence them, then you can imagine that you have like each variable has one dimension that you can change and that can change, and you have to integrate over all of them. And you can imagine it's rather easy to integrate over a circle. It's also possible to integrate over a circle, but what you see is that the number of elements that you get if you want to add them each of them up is kind of exploding. So with every dimension you get an exponential increase in the number of elements you have to integrate. So this is what we typically call combinatorial explanation, combinatorial explosion. And one classical solution to cope with this is to say, okay, actually I don't have to count each and every one of these little particles. I can also do like randomly picking samples, and one solution or one example for this is that if you take, if you want to determine the value, the numerical value of pi, then this is typically you can say, okay, I take the length of a square and then divide it by the kind of by the area of the circle. And you can approximate each of these areas by just throwing kind of random stones at the wall in the same region, and then count how many of those are outside and how many of those are inside. And this will give you kind of the ratio between the square, where you know how to calculate the area, and by the square area times the ratio you get out, you can determine pi. So that's what we typically call Monte Carlo simulation. And now the question is, okay, how? That's kind of also a technique you typically use in risk analysis. Is that you draw a couple of samples. You have to make sure that your random distribution describe your problem very well, and then you can get at least an approximation of what your expected value will be of your portfolio in the future. And now the big question is, how can I actually do this with a quantum processor? And the idea is that actually your quantum processor also has some very inherent probability. So you remember it can take like a continuous number of values, and kind of the very basic idea is that you use this randomness and the continuous values also to sample kind of from your portfolio, and from the variables that determine your portfolio, and the end result, which is very theoretic, is a circuit that looks like this. And I'll try to get into the details of what are each of those components. So in the end, I hope we get a little bit closer to understanding why this algorithm actually helps you, which is called amplitude estimation algorithm, helps you to get an estimation of some risk measures. So the first part that we need is the so-called Grover search. And what Grover search does is actually you're looking at a problem, for example, finding a book in your library that is marked. For example, you're looking for a book that has the citation in it, for example, from Feynman. I think I can safely say that nobody understands quantum mechanics. So what the quantum algorithm now does, and this is again referring to this continuous two numbers that describe your quantum bit, which are actually called amplitudes. That's just a name that physicists stick to it. You can imagine that either you can represent the book by, or the state of your book is the marked element, and every other element is the bad element. So you have kind of a good state when you found the book, and a bad state when you're looking at something else that is something different. And actually what you want to do, and now I can tell you that these amplitudes actually, they define probabilities that you measure the state. Yeah, so it's physicists found out that actually if you square these amplitudes, you get the probability that the state, that this good state comes out. So what your goal is in the whole algorithm is to start somewhere, yeah, with kind of a random initialization of these amplitudes, and then increasing the amplitude of the good one, yeah, so that in the end you get out, okay, here's the good part. Yeah, remember this this blob that comes up. So how do I do this? We can start for the first time with 3 qubits, yeah? And you're looking for something where, let's say, the first qubit is 1, and the second 2 are inverse to each other. Yeah? They're not the same. So to actually do this, you can create a couple of registers, yeah, and not going too much into the details, but these you can create any kind of circuit. Then you add a so-called X operation, which just flips between 0 and 1. And in this way, you can kind of, on the very basic registers, you can implement any kind of state. Yeah? And if you go onto the IBM website or any other solution provider, they will show you what each of those gates does. Yeah? But in principle, you have gates that turn the arrow around this sphere, and you have gates that actually couple them. So if you've done this, you actually create, in the next picture, oops, I think you don't let it run, right? I'm not sure if you, maybe give this cell a try, but a little bit further. And then it would be good to go in this direction. Okay, so maybe you can, there should be a picture popping up if you go a little bit further. So this is all just pre-definition. Yeah? What's really interesting is coming here. Yeah? Move it. You create a quantum register, a classical register with 3 qubits, and then you start to build your Grover circuit. And I'll show you a little bit later what this really means. If you go a little bit up, this is the final circuit we'll do, and we'll look at each of the parts what it actually does. Yeah? So we start with the first part, going up with it. Okay. So very good. Yeah, the first thing that we want to do is actually we want to as we said, yeah, we look for some state where the first qubit is 1. So these are these 3, and this one actually, and the other 2 are not the same. Yeah? So this drops out. So we want to have kind of the maximum amplitude at this point. And did a little experiment. Yeah, actually, if you this is kind of a simulation of what it looks in the quantum computer, but what you measure in the end is the square of this one. Yeah, so you here it's 0.707. If you square that, it's exactly 0.5. So in 50% you get this state, and in the other 50% you get this. Yeah? So that's kind of what we're looking for. Okay, so next. Now we have to build something. That's actually the one that creates kind of this solution. Yeah? So you can do an X gate. You do an X gate on the first qubit that switches it from 0 to 1. You always start at 0. That's just convention. Then you have another one that creates equal superposition. So it's half the time in 0, half the time in 1. And conditionally on what happens here, it switches the other qubit that has been switched before. So you're 0, 1, and the other one is always the other direction. Yeah? So we have kind of created the state, and now we can look. You can look at these qubits in this qubit state. So you have switched the first one, and the other ones are completely random between 1 and 0. Yeah? So they're in the middle because they're averaged. So that looks fine. And now actually, you remember I told you before that we have kind of defined a good state. Yeah? So here we measure how big the part of the good state is, or what's the probability amplitude. And on the other axis we measure how good or if it's the bad state. And you can either be in one or the other. Yeah? So it's kind of normalized. And now this arrow, what I show you here, is kind of that we take this first state and we look at how much of it is a good state. Yeah? And the arrow shows the whole way into the direction of the good state. Yeah? So we're completely right. So this is what we want to have in the end. Yeah? That's our goal. Okay, going a little bit further. So now we start our grower algorithm. Yeah? And to start, we need like any starting point, and physicists really love to initialize it in a superposition of all states. What does it mean? It means that you apply a Hadamard gate to each of the qubits, and it's your kind of quantum register is in the same state with same is in each and every possible state with the same probability. Yeah? So it's flat. Okay. So how good does that look? Yeah? You can do the same projection I've defined before and see how much of a good state is in it. Yeah? And maybe you have guessed this a little. It looks more into the bad direction than in the good. If you go a little bit up again, you see, yeah, a little bit up more. So actually, yeah, if you count how much of the blue stuff is looking into the good direction, it's only those two, and the other ones are much more. So that's kind of intuitively a good thing. So what do we have to do to get to the better states now? So the first thing is we do an operation that is not possible classically. Yeah? We switch the amplitude. So we have something that behaves like a probability, but actually the funny thing is that it can have a minus sign. And you can create an operation that flips the minus sign only for the elements that give you or that fit to certain conditions you tell them. Yeah? So you created something that doesn't know which is the right solution, but it checks, does it have this property and does it have this property, and then it changes the phase. So here we've inverted this, and that's kind of the first grower. It's phase inversion. And actually, you don't have to code in every single gate of this. There are already kind of predefined functions that give you this kind of operation. Yeah? So a good thing, you can actually abstract a little bit away already. Yeah? So how does this look in our good back picture? So actually, what have we done? We have switched the phase of only the good phases to negative. Yeah? So what happens here? Because this is also showing an amplitude, the bad direction or the part that looks into the bad side is still the same. Yeah? It hasn't changed. But the other ones gave a minus sign, so we're just kind of mirroring around this good axis. Huh? Okay. So did that help us? Not really, yeah? Because the part of if you project it onto this good axis, yeah, it has the same height. So you would say, okay, that doesn't make a lot of sense. But let's have one more operation that we define, and this is also something that you can do on a quantum computer, but not on a classical one. Is that you invert around the mean. Yeah? So you sit down and you add each of these elements up and calculate the average, which is exactly this line. And now you can do a mirroring against this axis. Yeah? And maybe you can see already the solution. Yeah? If I take this and mirror it here, it's 0 over the whole part. And now if I take this part and mirror it here, it actually comes out, so it's like 0.35 or something. Here's 0.35. Yeah? So probably something around 0.7. Yeah? So you do this operation and you see, well, I've only done 2 quantum operations that of course are kind of inferred by a couple of quantum gates, but after the 2 operations, I've already come to my solution. Yeah? Finding kind of 2 books in the library out of 2 to the 3, which is 8. So that's really strange, because typically you take like 50% of the solutions. Yeah? If you're looking for a book within 10 books, then you on average have to look at half of them. Yeah? This is less. And that's kind of the really funny and interesting thing about this quantum algorithm that makes people think that it's probably helpful for something else. And now we can do the projection again, yeah? And actually what this operation does is it mirrors against the original state that you've initialized in, yeah? So you see you've mirrored down here, and then against this axis, and you're completely in the correct direction. And you can repeat this for many more registers and find out it's actually a square root of n faster. Yeah? So you're converging much faster, and it becomes very relevant if you're looking at, for example, 100,000 books and more, 1 million books. Yeah, then you only need to look at 1,000 of them. Little disclaimer here. Yeah, actually the tricky part is in initializing your library within a quantum computer, which typically takes longer. So that's kind of a challenge you have to solve if you want to apply this algorithm. Yeah? Okay, and I've already in advance let this run on a quantum computer. Maybe the picture is still there. Go down a little bit. Yeah. So you see, yeah, it's not perfect. Yeah? So it's 35% and 33%. But you see already on real hardware, yeah, you can get, if you pick the two biggest solutions, you're right, yeah? in most of the cases. And of course the simulation tells you, yeah, you should only get these two. But how does that now help with quantum risk analysis? So the point is actually, with this algorithm you can do even more. Yeah? You can I told you before, you have this amplitude of a good state and the amplitude of a bad state, and there's actually a quantum algorithm that estimates, if you initialize any state in the beginning, like the superposition, that estimates how big this good state part is, yeah, in very few operations. So if you have a very bright idea of how to encode your expectation function or value at risk or any kind of risk measure in this amplitude in the beginning, you can do a very quick sampling and estimation of how big this is within a given time. And the idea behind this is actually to do more of these global operations. Yeah? So we have done the inversion, and then the phase inversion, and then the inversion around the mean. And this was only one operation. Now let's have a quick look. Yeah, what happens if you repeat this? Yeah? If you go a little bit further. So we started. Well, that's strange. So that's kind of the first Grover step. Yeah, the full algorithm of those two steps brings you already to the solution. Yeah? If you now do this again, yeah, so you actually mirror around the original state. And then around the other, you actually recognize that you get, after two Grover steps, you get back to your original solution. And if you do it again, you recognize, okay, this thing does nothing else than just alternating between the two. And this is not always the case. This actually depends on where you start. If you start a little bit further down, then your operation after one circle doesn't get you to the solution and back, but you take a couple of more iterations and a couple of more intermediate solutions before you get back to this. And this is actually telling you that this kind of matches some amplitude to a period. Yeah, so you can give every amplitude a period of kind of a number of operations that you have to do to get back to the original state. And that's something very interesting, is actually that next to Grover, there's a second big, very important quantum algorithm which is called quantum Fourier transform. And this quantum Fourier transform can perfectly assign or can perfectly detect or compare kind of frequencies, let's say. Yeah? So you have some periods or some operations that repeat itself, and the quantum Fourier transfer can, in very short time, determine what this frequency is. Yeah? So if you want to now implement this this amplitude estimation, what we have to do, we just do a couple of Grover repetitions, and then we see with quantum Fourier transform how long or what's the period of it to get an estimation of this amplitude. So what you can do now, if you go a little bit up again, now you can think about building a very simple model that models some risk case. Yeah? So for example, you have some random variable that arbitrarily switches or has influence on your portfolio. For example, if you have like good or bad weather, it probably will change how good the returns of your fields are that are out there. And you model this by 2 qubits. And you give them some variation, so you show how bad can it actually be. And what you do here is just to create some kind of, what you want to do is to create some distribution. And you define for 2 different assets what the probability of default is. So how likely is it, if I look in 1 year, that they won't be able to pay back. And what's also the case is that typically this value you don't know exactly. So there's some random distribution around this source. Sometimes it's a little bit more, it's a little bit less. It's because you don't have typically enough data yet to really describe it. So you actually take this average value and you say, okay, around this it varies like 0.1. And to know what the impact is, you also have to say how much you lose if they default. So in the end, what you want to know is I have those 2 that are influenced by a random variable, and on average for the asset, if I invest in both, what kind of loss will I expect? So the first thing that you do is to represent this model with the variation and the average in that's called GCI, Gaussian Conditional Independence model, and that's already one of the functions that is implemented within Qiskit, and you just have to tell them what's your average, how broad is the spread, and tell them each of those default values and how uncertain you are. And what it actually gives you back is some encoding of how you can represent your data on this quantum computer. So we did the first step, getting from the classical to this wobbly quantum state. And you can also map what it does. And actually the funny thing is, I don't exactly understand what each of the gates there does and why it does it. And you also don't have to understand, because you're drawing around and it's abstracted away from you that you can play around with it a little bit. So let's just ignore this. And actually in the next line, what it does is just calculating, given the random distribution that you have created in your quantum run, what would be the classic? So you do a classical simulation, like you do a lot of times, because it's easier to validate if you're going in the right direction. A little bit further down. So in the end, you have modeled kind of the uncertainty of those 2 variables by a very bad Gaussian distribution, very roughly with 2 qubits. And what the actual outcome is that you have some combined loss of those 2 assets and some estimated value. So kind of the tipping point where each of the values weighted by their height are in the middle somewhere. And there are a couple of other measures that tell you, besides what do I have to expect on the average, there are also values that tell you what kind of can happen in the worst case, or if I'm looking only at the 5% worst cases, how much is the loss on average. So it's kind of the expected default. So we've kind of modeled now the data on our quantum computer, and now what we want to do is to implement or to encode this weighted average, so the mean, on your quantum computer, and therefore you also use a predefined function which says you have kind of a weighted sum operator, and this encodes the expected value in your amplitude in the beginning, in the good state. So you're doing this, and you also have just to call a function and tell them the required qubits and a couple of values like the loss given default. And you go a little bit further. And after that, we run this. Now we have encoded it. We now run the algorithm that does the Grover steps for a different number of qubits, and then determines what the period is with quantum Fourier transform. And you can have a look at what the outcome of this is over here. So in the end, you have encoded, so you remember, you have like a good and a bad state, and here this tells you what actually the amplitude is you have encoded. One step that you have to do is actually to map it on a space from 0 to 1, because a qubit can only be between 0 or 1, or the probability, and actually this peak here tells you what is the most likely amplitude you have. And in the next step, you just map it back to the original values. So you remember up there was a loss function that had a peak a little bit next to 0, and then went down and a little bit up here again. So actually, what the quantum simulation that we did gives you back is a peak exactly at the expected loss, and the red line is what you would expect. And what you can see now that actually the result depends a lot on how many qubits you use, because this tells you how precise on this line your spin spacing is. And on the other hand, there's of course also the topic that if you don't do this on a simulator, as I have done it, you have probably a couple of values that are out of this typical range. So I started a job a while ago. Maybe. Okay. Yeah, actually, there are a lot of people who want to try this. So you still that's a kind of a small resource that a lot of people are asking for, and sometimes you get this interruption, especially if you want to use the bigger circuits. So what I hope that you can take away from this is actually that with those quantum computers, there are a couple of ideas of how to calculate something sensible, and it looks like very different from what you typically see. But in the end, you can roughly approximate it with a quantum computer, and the story is that you can do it in a quadratically or exponentially faster way. And actually, you have just to open this notebook or go on any side of the providers, and you can play around with these algorithms using a couple of abstracted away functions where you don't need to know like how the details of it work. So we are currently going into the direction of making this more useful and understandable, and trying to explain subparts of it in a more intuitive way. Okay. No, I stole all your time.
It's okay. So I would want to show like one last slide, Niklas, which symbol do I need to click? Yes, so there would be also some business explanation where we could go further into detail, but what I want to show you as well is some names that are already looking into quantum computing. And to be honest with you and to have a small disclaimer, those are companies that are publicly talking or somewhat doing somewhat with quantum computing, but not necessarily something which is going deeper into the direction. But I think at least it's very interesting to see that a lot of the DEC 30 companies in Germany are doing something. So some of them are publishing, for example, a blog on quantum computing. Others are, for example, Merck is doing something together with HPS, who was also a guest here. So they are investing quite significantly. Siemens as well, Deutsche Telekom, for example. I mean, Tim can also give some more insights there, but they also visited, for example, I think D-Wave in the Silicon Valley, and are looking deeper into it. Infineon is actually building chips, and I think, for example, E.ON is a case where also like a daughter company of E.ON was doing a workshop together with Tim. So I think it's quite interesting to see that a lot of German companies at least have the topic on their radar, and yeah, probably there's more to come.
And also, I think they're kind of pointing in a similar way that James does. Yeah, they're not doing this because they expect like in the next year it will help them to boost their business or so, but really to get a feeling of how differently this stuff works. And I think what is really interesting in the end is that there's a lot of theories how these quantum algorithms are faster, but in practice, sometimes if you have a new heuristic, like just a little bit different way, you have for a couple of problems that have a certain mathematical shape, or like I mean, probably you remember the sorting algorithms. How fast your sorting algorithm is, it doesn't only depend on the theory how quick it is in the best or the worst case, but actually there are kind of a lot of specific cases where it can be really good or bad. So in practice, I think it really makes sense to try out these algorithms, and I think that's also what you are doing at US Quantum, trying heuristics and other algorithms that are not fundamentally proven faster, but that could be. And I think with this hardware, it's very interesting to find it out where this can happen first.
So, any questions so far?
I don't know if we should use the box again.
Any questions?
So you motivated the example of the sorting algorithm, like with 3 qubits. So if you want to search for bigger in a bigger dictionary, maybe, so you need to scale up the qubits probably. So is it possible? So at some point you don't have much more qubits. So can you repeat the algorithm, and at some point it converges with fewer qubits, or how would you scale it up to bigger problems? Or is there actually a solution to this?
It's so that's actually one of the big advantages is that if you add 1 qubit, you double the number of states that you can represent. So actually with 54 qubits already, you have a state space of 2 to the 54. So that's actually something where if you do it naively, you would need the whole memory of a supercomputer, of the best supercomputer of the world, to really represent what all of the states are. So you're kind of getting very quick to being able to represent theoretically a lot of data. The big challenge is how to get it into your quantum computer. So it's not very efficient to represent like a big amount of data in a quantum computer. So there are definitely challenges. And you're right. The other topic is that's also very. I mean, doing my PhD thesis, I built like not even 1 qubit, and it was hard enough. And there are a lot of people who are trying to build more, and this 54 is really that all you can achieve in a good quality. So, but actually, if you look at the last years, there's already like a first indication that this is going further and further. And I mean, I think Google, IBM, and Microsoft, all the big players are pushing very hard, putting a lot of resources into it, and it looks like the scaling is continuing similarly to the exponential increase with classical computers. But very early to say.
Okay, another question? Maybe afterwards with a few beers.
Dean is not sure yet.
Yeah, I'll just ask a question. It's regarding search
There are no bad questions, so please.
So, I'm curious about the search algorithm. You think that you can use it to improve the speed of SQL searches, SQL queries?
So, actually, like, one of the disadvantages, of this representation is that, I mean, typically you have like a random data, you have some representation of your data, and you want to query it for different things. If you use quantum memory, you can do this only one time. So that's actually, that's one of the things. There are a lot of disclaimers there, and I think that's something where you have to really find out where this would make sense to help. So for most applications, and that's the reason why we are currently kind of nobody is gaining a kind of having a business concept from calculating stuff with a quantum computer directly. It's like currently developing an idea of which direction to go to really make it useful. And Grover, actually, the choice of Grover is mainly because there's at least some intuition how to visualize it and to understand why it's faster compared to other algorithms that are even more complicated. So the choice of algorithm here was more to have like a good visualization.
So, another question? Tim or Felix or anybody else? All right.
Just as a question.
Easy questions are the best.
The example that you show us with assets or represented, what, like, in a simple language, what is it like benefits or what is it different from standard trees?
So what you typically do today is that for some portfolio, you calculate a lot of scenarios overnight. So you do a whole night calculation for only the portfolio that you already have, just to get an idea of. I mean, typically it's good if you can predict how this will behave, because then you feel safe. If you have a very big uncertainty, it's a big problem, because you don't know if you should hand out more money for people that can do something sensible with it, or you should withhold it to make sure that in the next day you don't go bankrupt. So if you can make this more certain, you can actually kind of be a little bit more safe to hand out like development credits or something like this. And if you have a quantum computer and you implement an algorithm that would kind of drastically reduce the time, you could also help decisions on choosing different portfolios. Do this for other portfolios and see maybe you should shift your assets where you invest, or you can just calculate more scenarios and be kind of even more sure of the solution that you get, of the prediction. With the disclaimer that also the data that you calculate on is somehow unsafe. So at some point it doesn't make sense to calculate further.
Does it answer your question? You have another question. All right. So I think Tim gave a good example what quantum computing or developing algorithms in quantum computing means, and what it can bring for the future. Very good problems can be solved, but it's a long way. So hope some of you got some information from this meetup. We're going to make the next one in 3 to 4 months. With some new speakers, and I would like to thank you for all taking part. For James giving a nice presentation about games, and for you guys about risk analysis. So thanks a lot. We're finished. Take some drinks and enjoy the rest.
Danke dir. So.